Hello, and welcome to our presentation on robust TRISO-Fueled Pebble identification by digit recognition. Pebble bed reactors are a class of nuclear reactors known for safety, modularity, and efficiency, using tri-isotropic fuel particles mixed with graphite and spherical pebbles. These pebbles continuously circulate in the reactor, undergoing burnup, and are refueled based on their burnup levels. PBRs have an advantage in efficiency as they do not require shutdown for refueling. Pebble identification is crucial to prevent excessive burnup, requiring unique identification for each pebble. A proposed method involves tagging pebbles with multi-digit numbers using ultra-high temperature ceramic paint. The problem involves identifying and timing each pebble as it enters and exits the reactor to calculate residence time. Computer vision techniques are proposed for accurate and automated pebble identification. Contributions include a novel tagging system using ceramic paint, the first computer vision-based system for identifying pebbles in motion, and a fast, non-invasive method to calculate residence time for safer and more efficient Generation 4 reactors. Some of the related work in this field includes X-ray imaging explored for pebble identification in nuclear cores, utilizing TRISO-Fueled particle distribution in 3D X-ray CT scans for unique identification. The challenges with this are that X-ray imaging include potential impact of gamma radiation on pebble integrity and limitations of testing on synthetically generated pebble sets. In addition, digit detection and recognition involve OCR engines and datasets like MNIST and SVHN for flat surfaces, not directly applicable to moving spherical objects like TRISO-Fueled pebbles. Recognition challenges for pebbles include arbitrary rotations, out-of-plane image warping, and motion-related blur, necessitating a novel methodology. Previous works on digit recognition do not address the specific complexities introduced by the unique characteristics of TRISO-Fueled pebbles. We created a benchmark dataset for TRISO-Fueled pebbles in this nuclear reactor application. We took 600 pebbles and labeled them with 3 digits using the ceramic paint. Stationary photos of each pebble with horizontally aligned numbers were taken. Then 2 training videos with 14 and 21 moving pebbles were recorded in the outlet chamber. Finally, a test set consists of 1 inlet chamber video with 43 pebbles and 1 outlet chamber video with 47 pebbles. This was all captured using a Panasonic 4K Ultra HD camcorder in a 1920 by 1080 resolution and 30 FPS in an RGB format. So our overall goal is to extract frames with valuable information for pebble detection and identification in a video stream. We do this in a multi-step approach. We frame breakdown to detect digit areas, horizontal alignment of digit areas, removal of blurry or heavily occluded digit areas, and finally classification of aligned digits using a digit recognition model. So our first task is digit area detection. We use a mask RCNN to identify digit areas in frames. We segment and save detected digit areas for processing, and we stop processing if no digits are present. Next, we do digit area orientation alignment. We detect orientation bars underneath each digit using a mask RCNN. Using this detected bar, we rotate the image to align the digit area horizontally for readability. We discard digit areas without detected orientation bars. Next and final step is digit recognition. We use a 10-class digit recognition model with mask RCNN. We recognize digits within the aligned digit areas. We enforce recognition to contain distinct digits with minimal overlap, similar to non-mask suppression. We implement a voting system for sequential recognition over multiple frames. And we stop repeated recognition once a pebble accumulates a confident number of votes for each digit. Our sequential voting consists of accumulating confidence scores through sequential recognition, and then stopping the repeated recognition for a pebble when it reaches a confident number of votes for all of its digits. So now we can evaluate the performance of our system. In terms of digit area detection, we have high precision and recall values at IEU levels of 0.50 and 0.75. And similarly, in digit area orientation alignment, we achieve high performance with accurate bar detections. Both of these steps facilitate easier recognition of digits later on, and they set up our problem so that we can perform the best on our system. Now, in terms of digit recognition, which is just individual digits that we are trying to recognize, we pre-trained our model on the SVHN dataset and then fine-tuned it on our multi-class digit dataset. This model outperforms other OCR models like Tesseract and EasyOCR when recognizing the digits. We also use CLAHE pre-processing for the OCR model so that they can perform best. Our model, in terms of digit recognition, is robust in motion blur and cutoff digits, and is adaptable to different Pebble digit styles. Now, in terms of overall Pebble identification performance, ours achieves the best results in comparison to using Tesseract or Easy OCR. We believe the extra knowledge from SVHN pre-training contributes to higher confidence individual digit predictions. And when we compare with our model with the different digit recognition models which are using OCR, ours performs best, and without orientation alignment, we significantly decrease performance, but this will be shown in the ablation study. So we believe that leveraging knowledge from multiple frames for confident digit recognition helps the model, and we can over time correct small errors, contributing to improved Pebble identification accuracy. So this is an example of pebbles being detected over a sequence of frames. A collection of predictions allow for slight errors to have little impact on the overall final classification. In the last column, we showed the normalized 10 class scores for each digit of the multi-digit number, and these scores represent the most probable digits that are concatenated and used in our overall Pebble identification. We also did an ablation experiment where we removed both the digit area detection model as seen on top, and then we also removed our digit area orientation. So when we remove the digit area detection model, we see that it is crucial for accurate alignment, as otherwise the model will not correctly orientate the pebbles. The second model will not correctly orientate the pebbles. And then in terms of removing the digit area and torsion alignment module and only keeping the digit area detection and digit recognition models, we can see that we can obtain digit recognitions, but since the digits can be seen as like completely sideways or upside down, we can get very poor predictions. So therefore, digit area and torsion alignment is crucial for accurate digit recognition and overall Pebble identification. In addition, it serves as something that removes extremely blurry images and aids in robust digit recognition. So the presented approach offers a comprehensive solution for TRISO-Fueled Pebble identification, leveraging a unique ceramic paint digit patterning system. Some key highlights include digit area detection and orientation alignment methods, enhancing identification robustness, and resilience to challenges like motion blur and rotations in pebbles rolling in video streams. We outperform OCR models struggling with digits on spherical objects, and we also overcome issues related to digit warping on curved surfaces. We create new datasets enabling adaptation of a model pre-trained on the SVHN dataset. And we have scalability demonstrated with the potential to handle large datasets for nuclear energy production. We're not reliant on X-rays, and instead we can rely on surface patterning as it remains intact in core conditions due to heat and abrasion-resistant properties. And we set up a potential for the next generation of nuclear reactors. We paved the way for innovative TRISO-Fueled Pebble identification methods, and we offer avenues for research and implementation in the next generation of nuclear reactors. Thank you for listening.